Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about the addition, subtraction, and multiplication principles in combinatorics and how do you know when you're supposed to use each operation. So let's start with the addition principle. If A things are added to a collection of B things, the total number of things is A plus B. So for instance, if we have 3 apples and 5 bananas, there's 3 plus 5 equals 8 fruits in all. So this looks like a very simple principle on the surface, but when we're doing counting problems, it comes in handy to keep in mind that when you see or in a problem, that might mean that you should use the addition principle and use plus. Because when you're counting objects that can be either of type A or of type B, you want to add the number of type A to the number of type B. For instance, if we wanted to know how many fruits are shown on this page, well, we could first count the apples, 1, 2, 3, and then count the bananas, 1, 2, 3, 4, 5, and then add them all together and get 8. And so if you see or in a problem, or you realize you can break the thing you're trying to count into different cases, that's a way that you can use the addition principle to count more objects. Here's an example. How many 3-digit numbers start with either 1 or 7? There's an or, so maybe we should use plus. So first we say how many 3-digit numbers start with 1. Well, starting with 1, there's 100, 101, 102, up to 199, all the ones that start with a 1, and there are 100 of those. Starting with 7, there's 700, 701, 702, up to 799, also 100 of those. Remember, it's 100 and not 99 because it starts with 700 and then 701, 702, up to 799. And so there's 100 starting with 1 and 100 starting with 7. The addition principle says that there are 100 plus 100, or 200 in all. Let's do a slightly more complicated example. How many squares have all 4 edges on this unit grid? So for instance, the little 1 by 1 squares would count, but also you can make, say, a 2 by 2 square by tracing along the edges of the grid. And you want to count how many possible squares can you find in all. Well, it might be good to break into cases. Now this problem doesn't have an or in it, so it's not telling us how to break into the cases, but we might want to break into cases by the size of the square. So let's count the 1 by 1 squares first. There's 9 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 3 times 3. And we'll get to the multiplication principle soon. For the 2 by 2 squares, there's a 2 by 2 square, and I claim there's 4 of them because you can draw this one in this corner, or move it over 1 step, or move it down, or move it over to that corner. And there's 4 in all. And then for 3 by 3 squares, there's only going to be one way of tracing out a whole 3 by 3 square on the 3 by 3 grid. So all in all, you add up these 3 possibilities. 9 plus 4 plus 1 is 14 squares in all. So there's how we broke a problem up into smaller cases where each case was more tractable and then added them up with the addition principle. Here's the subtraction principle. If B things are removed from a collection of A things, then there are A minus B things left. For example, there are 8 fruits here, and say you eat 3 of them. You like the apples, but you don't like the bananas. How many are left? 8 minus 3, or 5. So the guideline for subtraction principle is that when you see the word not in a combinatorics problem, you might want to think that it's the subtraction principle, because you're taking away things that you don't want to count. For example, we could have phrased the problem as how many fruits are not apples in this picture. Well, then it's just all the fruits minus the apples, and you have the bananas left. Let's look at a little harder example of the subtraction principle. How many 3-digit numbers between 100 and 199, so those are the 3-digit numbers, do not start with 2? So we have a not here, and that's an indication that we want to subtract the number of these that start with 2 from the entire number. So first we have to count how many total numbers are there between 100 and 999. And the trick here, if you want to know how many numbers starting from one number and ending at another, is you take one less than this number, 99, and you subtract that off. And that's also by the subtraction principle, because there's 999 numbers from 1 to 999, and then there's only 99 from 1 to 99, and you get rid of all those, and what's left? The numbers from 100 to 999 exactly. So we subtract off that 99 and we say we have 900 3-digit numbers total to start with. And then we want to subtract off the ones that start with 2. Well, there's the ones from 200 to 299 are the ones that start with 2. And as we calculated in the 100s and 700s case, there's 100 of those. And we put those together. 900 minus 100 equals 800. So by the subtraction principle, you have 800 3-digit numbers that don't start with 2. Now let's get to the multiplication principle. And this is the most important principle in combinatorics. It is the foundation of everything we're going to be building up. We need to know, what does times mean when you're counting? So the multiplication principle says that the number of ways to make one of A possible choices and then one of B possible choices is A times B. So here's an example that really illustrates why we multiply. Say you have 5 shirts and 3 pairs of pants that you're choosing between for an outfit. How many outfits can you make? So here's 5 shirts and 3 different pairs of pants, and notice each X in this grid denotes an outfit, 1 shirt and 1 pair of pants. And you can mix and match in any way, but how many ways can you mix and match? Well, it's the number of X's in this grid. And when you have a 3 by 5 grid, we know it's going to be 3 times 5, or 5 times 3. So the number of ways you can pick 1 shirt and then pick 1 pair of pants to go with it is 15 in this case. So the guideline here is that when you see the words and then, or you think of them, that means multiply. If you make one choice and then, given that choice, you make another choice, you multiply instead of add, and you'll get the total number of things that you're counting. So here's another example. How many 3-digit numbers have all odd digits? This is a very good example of where the multiplication principle will come in handy if we just try to count our choices 1 digit at a time. In particular, what are the odd digits? Well, an odd digit is either 1, 3, 5, 7, or 9, and the 3 digits can be any of those. So there's 5 choices for the first digit, and then there's 5 choices for the second digit, and you also have to choose one of 5 digits for the third digit, and once you've made those 3 choices, you have chosen a 3-digit number. And so we get the answer of 5 times 5 times 5, or 125 choices for the 3-digit numbers with all odd digits. And that's not easy to count with the subtraction principle. We can't just sort of subtract the ones that have an even digit. That's actually harder to count. Not good for the addition principle either. The multiplication principle really was essential for this problem. Now let's think about how we can combine the principles, and this is important for when you're just faced with a problem and you just want to count something. You might have to use different principles together and combine them all to solve the problem. Here's an example. How many 3-digit numbers are there such that all 3 digits are the same parity? Parity means even or oddness, so either they're all even or they're all odd is what this problem means. And so say they all have to be the same parity, but the units digit cannot be 7. Okay, so there's a not, so we should probably use the subtraction principle. But parity can be even or odd, and so there's probably the addition principle. And also, when we counted the ones with all odd, we used the multiplication principle. So this problem is going to take in all the principles and put them all together to solve it. So let's do it one step at a time. Let's notice, first of all, let's build on our previous problem. We found before that the number of 3-digit numbers with all odd digits is 5 times 5 times 5, 125. But we want to eliminate the ones that start with 7. We only have to subtract those from the odd case because 7 is odd. So if it's all odd but 7 is the units digit, that means there's 5 possibilities for the first digit and 5 possibilities for the second, and 7 has to be the last digit, and so there's actually 25 of those, which we have to subtract off because we're not allowed to start with 7. So this is where we use the subtraction principle for this not. 125 minus 25 is 100 valid all odd possibilities in this problem. And then let's do the even case. So in the even case, now we have to be a little careful. The first digit can be 2, 4, 6, or 8. It can't be 0 because otherwise it wouldn't be a 3-digit number if it starts with 0. But the other two can have 0, and so there's 4 possibilities for the first digit and 5 possibilities for each of the next digits. And we have 4 times 5 times 5 is also 100. So actually there's 100 odd and 100 even, and altogether from the addition principle we get 200 possible 3-digit numbers that satisfy these properties. So now you try to combine these principles. How many squares whose edges lie on this 5 by 5 grid do not have the same center as the full square? Meaning the center is right in the middle of this square here. Think of a little center dot there. And you want to count all the squares that you can trace out on this grid as long as the center of that square is not the same as this dot in the middle. So there's not, so there might be a subtraction principle involved. You could do cases by size, so there might be an addition principle. Maybe there's multiplication, but thinking of grids 5 by 5. And so think about how you can combine all the principles to solve this problem. And I'll see you next time.